Hi again. We know a lot about the Laplace transform. We know how to compute the Laplace transform of a great variety of functions, including periodic functions. We even know under what conditions a function has a Laplace transform. We mentioned in the beginning that when we have a linear ordinary differential equation, it is possible by applying the Laplace transform to obtain an algebraic equation. And we also said that it might be difficult to obtain a solution directly, but somehow I promised you, so to speak, that these algebraic equations are useful, but we haven't figured out exactly how to use them so far. We only know that the Laplace transform of the derivative of a function is given by this formula. Today we will solve 6 exercises. In the first 3, we will be looking for this value. This value is really valuable because it provides some information about the solution, namely its initial value that we will be able to obtain without solving the differential equation. We will only use this algebraic equation. In other words, we will use a function in the S domain. We will use a Laplace transform. Other than the initial value, we are also looking in the last 3 exercises for the final value. The final value is this value, f at infinity. F at infinity is a shorthand notation for this limit. Instead of writing this limit, we can write f at infinity. And we will be able to obtain this value without without the need to determine the solution, just using the Laplace transform. So now it turns out that the Laplace transform provides very useful information about the solution of a differential equation. It turns out that function f uppercase can tell us some things about function f lowercase without the need to determine this function f lowercase, although it is not impossible. But we will do that actually very, very easily. Using this very little trick. When we have a function g in the S domain, which is a Laplace function, so if g uppercase is the Laplace transform of some unknown time domain function, then the limit of this g as s goes to infinity is always equal to 0. So if we take a limit as s goes to infinity on both sides of this equation, we'll have the following. And we arrived at this equation, which is a very useful result. This is the initial value theorem. And look why this is important, because it allows us to obtain a limit for that time domain function f, which is utterly unknown, using the Laplace transform of this function f. And this allows us to solve very easily exercises 1 and 2. So exercise number 1, we have that f uppercase of s is 1 over s plus 1. This is the Laplace transform of some unknown function f lowercase. Well, in that case, f uppercase is simple enough, so we can figure out what f of t is. This is a familiar Laplace transform. It's an easy one. It is in fact e to the minus t. If you apply the Laplace transform on e to the minus t, you obtain this time domain function. And you can tell from here, of course, you can determine f at 0 plus, which is equal to 1. But this is not what we want to do, because in the general case, function f lowercase can be very difficult to obtain. So we will use the initial value theorem. f at 0 plus is equal to the limit. We cannot find the value yet because this is infinity divided by infinity, but this is not a problem. If we divide both the numerator and denominator by s, we arrive at this expression, and clearly now the limit is equal to 1, which is the same value as what we found before, only now we didn't need to determine this function f. So we have f at 0 plus without being able to find, without the need to find f lowercase. And this becomes more evident in this second example where f is more complicated, is a more complicated function. Now it is not that easy to find f lowercase, it is not impossible, but it's quite cumbersome. We'll figure out how to do that later. Now this is again infinity divided by infinity. In fact, we can write the numerator like that. It's clear this goes to infinity, this whole thing goes to infinity. We cannot yet compute the limit, but if we divide both parts of the fraction by s squared, we will see that the numerator goes to 5, the denominator goes to infinity, 5 over infinity goes to 0. So this solves the second exercise. The third one now. Again, we will use the initial value theorem because the exercise is asking for an initial value. Only now the difference is we're not looking for the initial value of x, but the initial value of x dot, the initial value of the derivative of x. In fact, we are given the initial value of x. We have that x initial is equal to 0, x dot initial is equal to what? And we will apply the initial value theorem. Let's write it like that. X dot 0 plus is the limit as s goes to infinity, s times the Laplace transform of that function. And we know that the Laplace transform of a derivative is given by s times the Laplace of the function minus the initial value. And we know here in this exercise that this is equal to 0. This is given over there. Now this becomes limit of s squared times x of s, where s goes to infinity and x of s is given over here. Let's write it once again. Times u. But function u is the Laplace transform of this input function, of this time domain input function, which is the Heaviside function with parameter a at t. And this is equal to e to the minus as divided by s. And we can put that here. And I will leave this to you to find the limit as an exercise. You will end up here with a single number, which is the limit of x dot as t goes to 0 plus. So this much about the initial value theorem. You can try one more exercise to practice. Consider that a dynamical system now is given in the S domain. This means that there is some ordinary differential equation on which we applied the Laplace transform, and this is what we obtained. So there is some ordinary differential equation involving x dot, x, u, perhaps u dot, and so on. And we applied the Laplace transform, and we ended up with this expression for the state, the Laplace transform of the state, and this is the Laplace transform of the input variable, and we know that the input is given by that. Find the initial velocity, the initial value of the derivative of x. And it is given that x at time 0 is equal to 0. So do this as an exercise. Okay, so we solved exercise number 3. Let's now go for 4, 5, and 6. Now there, we need the following result. We need the final value theorem that provides f at infinity. The theorem states the following. If this is proven in a similar fashion as the initial value theorem. There are some differences, and the theorem states the following, that if certain regularity assumptions are satisfied, we don't need to go into details, and f at infinity exists. Now this is a little strange because the theorem requires, before we know the value of f at infinity, the limit of f at infinity, it requires to be able to tell that it exists. And it is finite. Exists, let me write, and is finite. Not infinity. Then you can compute it using this formula over here. It is like the initial value theorem. The only difference is that 0 and infinity are swapped. So plus infinity goes here and 0 plus goes at the limit. So it is s goes to 0 plus over the real numbers, s times f of s. But the question is, how can we know that the limit exists? If we know that it exists, we can plug it in this formula and obtain a result. But in the first place, how do we know that it exists? And there is this little result that says that if function f is given by a rational function, polynomial divided by polynomial. For example, (5s plus 1) divided by 3s squared plus 5s plus 2, and so on. Or even 1 divided by s plus 1. This is a rational function. It is a polynomial of degree 0 divided by a polynomial of degree 1. Polynomial of degree 1 divided by polynomial of degree 2. So if it is like that, and the degree of the numerator is smaller, not equals, smaller than the degree of the denominator, and now something about the denominator. Something about the denominator, Q uppercase here. If the denominator has some roots which are in the open left part of the complex plane, if all roots of this polynomial Q have a negative real part with a possible exception of one root at 0 with a possible exception of one single root at 0, then this limit exists. Once again, if f is a rational function, if it is not a rational function, let's forget about it. We can't say much, or at least it's not so obvious if this function is not rational. If it is rational, however, which is a very, very common case, and it is a polynomial divided by another polynomial, and this is a low degree polynomial divided by a large degree polynomial, like this, small, large, all right? And focus now on the denominator only the denominator. Now find the roots of this polynomial. The roots are called the poles of the roots of Q are called the poles of F uppercase. So find these roots. If they all have a negative real part, for example, are negative numbers, or they are like minus 10 plus minus j. We don't care about the imaginary part, the real part, this part. If the real part is negative, then the limit exists. If it is like that, and there is an exception, there is one single root at 0, then this is still fine. But I think it's best that we apply the theorem and see how it plays out in practice. Here we have a polynomial of degree 1 divided by a polynomial of degree 3. This is degree 2 times degree 1, degree 3. What is Q? What is the denominator? What do we have here? Apparently we have that 0 is a root. It's a single. Of Q. But this is okay, this is allowed. This is fine. It's not a double root, by the way. If we had a square here, that wouldn't be allowed. That would be a double root. We have a single root, which is fine. Then what about this part? S squared plus S plus 1. What are the roots of this part? Well, let's figure out. One squared minus 4 times this coefficient times this coefficient. 1 minus 4 is minus 3. And the two roots, let's call this root S1 is 0. This is the first root, so these are the second and the third root. Minus 1/2 plus minus j times something. We don't care about the imaginary part. We care only about the real part. The real part is negative and this is allowed. So we're fine. We're good. We can apply here. We can apply the final value theorem. Two roots with a negative real part, one root at 0, we can apply the final value theorem. This goes to 0, so this goes to 1. And the answer is 1. F at infinity is equal to 1. And that's the answer, and we have solved this exercise. Very good. Exercise 5. S plus 5 divided by s to the third power, s cubed plus 6s squared plus 11s plus 6. This is a polynomial. Degree 1, degree 3, so far so good. It only remains that we determine the roots of the denominator of this polynomial. We need to determine the roots. The problem is this is a third order polynomial, so it's not so easy to find the roots. However, we might notice here that if we plug into this polynomial the value minus 1 to the third, six minus 1 is 5, 5 minus 11 is minus 6, plus 6 is equal to 0. So we figured out here that minus 1 is a root of this polynomial. Minus 1 is fine, so far so good. Another 2 roots to go. We have one root. This is a third order polynomial. According to the fundamental theorem of algebra, a third degree polynomial has 3 complex roots. How did we come about? How did we come up with minus 1? Well, we just selected numbers here. We can always select numbers that divide. So one way to start is to try to find to try numbers that divide the constant term. So good candidates here are, because all coefficients are integer numbers, a good start is to try numbers that divide the constant term. So 1 minus 1, 2 minus 2, 3 minus 3, and 6 minus 6. Somewhere around there might be a root. No guarantees, however. Any positive numbers are out of the question here because we have all positive coefficients. So it cannot be that you plug in a positive number and you obtain 0. So we're looking for a negative number. So it makes sense. We're looking for minus 1, minus 2, minus 3. So a good starting point is to try some of these numbers. And the first one we tried, minus 1, turned out to be a root. Now what do we do to find the other 2 roots? We'll use Horner's scheme. Horner's scheme. It goes like that. Write down the coefficients of this polynomial. So numbers 1, 6, 11, 6. 1, 6, 11, 6. Next to them, write the root that you have already found. In our case, minus 1. And then draw a line here, draw another line, and some vertical lines. Now it's very simple. What we have to do is that we write 1 again here, we copy it here, and we multiply it by minus 1. Minus 1. And we add these two together. 6 minus 1 equals 5. And then again, 5 times minus 1 is minus 5. 11 minus 5 is 6. 6 multiplied by minus 1 is minus 6. 6 plus minus 6 is equal to 0. 0. It must be 0. It must be 0 if the number you've put here is a root. If it is not 0, you've done something wrong. Okay, now. Therefore, we have the following, that Q of S is equal to S minus the root, so S plus 1, times that, times 1, 5, 6. 1, 5, 6. I mean 1s squared plus 5s plus 6. So now the roots of Q are minus 1 and whatever roots come from this polynomial. And this is why now Horner's scheme is very useful for finding roots of third, fourth, fifth, and so on order degree polynomials. And if you do the math here, you will find that we have 2 roots. If you obtain the discriminant and so on and so forth, you will find that the other two roots are -2, -3. So this is negative, this is negative, this is negative. All the roots of this polynomial are negative. And this is great news because we can apply the final value theorem. All roots are negative, we can apply the final value theorem. And here it goes. So it is 0 times 5, let's write it here, 0 times 5 divided by 6, which is 0. And we have solved this exercise as well. The last one now. Exercise number 6, it asks for a final value. Again, it asks for the limit of x at infinity, x at infinity. Again, this is a shorthand for the limit x of t goes to infinity, and the question is this is equal to what? And we have the following differential equation, 2 times x dot plus x equals 3 times u. I forgot to mention here, I have to provide the initial value. X at 0 plus is equal to 0. We need that here. If we apply the Laplace transform, we have 2 times s times x of s. It is actually minus x 0 plus, but we said that this is equal to 0. So it is just 2 times s x of s plus x of s again equals 3 times u. Let me write it again. 2s plus 1 2s plus 1x is equal to 3 times u. But u, as a function of time, is the Heaviside function. And the Laplace of the Heaviside is this function, e to the minus as divided by s. Now x of s is given by this function, which is not a rational function. This part is a rational function, but it is also multiplied by an exponential of minus as. In that case, the final value theorem still works. We can still apply the final value theorem, so long, of course, as the limit of x at infinity exists. How do we know? We have to look at the rational part and find the roots, find the poles of this rational function, the roots of the denominator. And we see this here very clearly. 0 is a root, and it is a single one. Zero is a single root. If we had a square here, we wouldn't be able to apply the final value theorem. And from here, minus 1/2, which is negative. So we can apply the final value theorem. And the answer is x infinity is equal to 3. Now, so we have solved all exercises, and that's it for today. One very important thing that we need to keep in mind when applying the final value theorem, if we say, okay, we'll skip the part where we check the roots, we'll skip the part where we check the poles of the rational function x, uppercase of s, of the Laplace transform function, then do not expect that the result will be something clearly indicative of the situation. Like, it is not that it will be equal to infinity if the conditions of the final value theorem are violated. It might be equal to 0 or 1 or 2 or whatever, but it will be wrong. So we must check the conditions of the final value theorem. Otherwise, there is no way to know whether the result we obtained is correct or not. So this much for today. So in summary, we solved this first exercise using the initial value theorem, then again here the initial value theorem, and again. The initial value theorem is a lot easier to work with. Then here we use the final value theorem. Here we use the final value theorem plus Horner's scheme, because here we have a third order polynomial and we needed to be able to find its roots. And in the final example, again we use the final value theorem. And with that, thank you very much for watching, and until next time, goodbye.